So the basic idea of HPCToolkit is really pretty simple. So we run your program natively, and by natively I mean optimized, and something like 100 times a second we interrupt the program and all of its threads and figure out where the instruction pointer is, unwind that back to main. That forms a path. We put all the paths together and that forms a tree. And then we present the tree to you in top-down, bottom-up, or a flat view. So when I tell you we interrupt the program and make a path and then make a tree, this is the picture that you should have in mind. So we take an interrupt like 100 times a second, makes a path on over here, put them all together, and you get a tree. Okay, so everything I'm going to be showing you is showing you this tree in different forms. But this is the picture that you should have in mind. Okay, now, in addition to running the program and interrupting it and figuring out what the call stack is, we also run a static analysis of your program using a program called HPCStruct. And what HPCStruct does is it adds loops and inline templates. So if you just unwind the call stack, you get function, function, function. But then but if you run an extra program, then you also get loop scopes and also inline sequences. So if anyone has used, C++ programs with heavy templates, then that's what it shows you. It'll show you all the steps in the templates. Okay, and then as I said, we take this tree and give it and present it top down and bottom up in a flat view. And one of the things that I'm going to emphasize is that all of the things that we display, all the measurements that we display at every node or every step of the tree. Maybe this doesn't make sense right now or something, but it might a little later. Now, when I say that we interrupt like roughly 100 times a second, it doesn't have to be necessarily on time. It can be on any of the hardware performance counter events using either the PAPI interface or the perf events interface. So all the native hardware events, which in the good old days, it used to include flops, but Intel is taking away flops or something. But things like cache miss, you can look for cache misses or TLB misses or something, or whatever the hardware will still let you do these days. And since I work for a profiling tool, all profiling tool speakers will tell you or should tell you, please always compile your program with debug information. Now, for our tool, you can leave optimization on, but you have to give it -G or else it just says, function hex address calls other function, it has a hex address and an unknown line number, which isn't very useful. Okay, so that's the basic idea. Now, some of the more advanced features are unwinding on x86 is really, really tricky. It's not so hard on PowerPC or ARM or something, but for x86, figuring out where the return address is challenging, doesn't really even begin to describe it. Now you might think that frame pointers solve the problem, but optimizers take away frame pointers. So the real trick is how do you do it without frame pointers or something? Okay, and so we spent a lot of time and effort on that. Now, one of the things that we can do is compute what we call derived metrics. So we can measure in the HPC runtime whatever sort of the hardware can measure, either time or flops or cache misses or something. But then to get these more useful, in the viewer you can make a derived metric. So you can take something like, well, if I'm able to count flops and I'm able to count cycles, then I can put these together and compute a number based on that is the flops per cycle, or if you're not doing very well, the cycles per flop. Okay, one example of derived metrics is that we could use scaling studies. So, for example, for a weak scaling, study, if you have, let's say you run a program at 1,000 nodes on some size of a program or some size of a problem, and then you run it, let's say, 8,000 nodes on a problem that's 8 times as large. So if you have perfect scaling, perfect weak scaling, then the running times of those two programs should be exactly the same, right? If you have perfect scale, you run it on 8 times as many cores on a problem 8 times as large. So what you can do is you can compute a formula that says, like, node per node, take the time at the large problem, subtract off the time at the small problem, and compute that difference, which will usually be a positive number because you don't have perfect scaling. And then you can present that and look at the program and say, well, this part scales well and that part doesn't scale well. But at every node in the tree, you can compute, what you've computed is the scaling loss just for that scope of the tree. Okay, so that's one example of using derived metrics. You can also look for load imbalance. Now, I'm not going to talk too much about load imbalance, but another technique that we've invented is something called blame shifting. Now, and this I am going to talk a little bit more about. So, now the idea of blame shifting is kind of interesting. So let's say that I'm an OpenMP loop, okay, and I have 10 units of work to do, and I have 1 helper thread. So I'm going to pick on you. You're going to be my helper thread, and I'm going to be the master thread. And I'm going to say, okay, I will take 8 units of the work for myself and give you 2 units of work. Okay, so what's going to happen? You're going to finish first. You're going to sit there twiddling your thumbs, and I'm going to complain, look, I'm doing all the work, and you're just sitting there idle. Okay, so should I blame him? Well, the answer is no. You should blame me for not breaking up the work better. So the idea of blame shifting is when we measure that a thread is sitting idle, you don't blame the thread that is idle. I mean, you could run the program and say, okay, this thread is sitting there idle, and so that's the problem. No, that's not the problem. I'm the problem because I didn't split up my work well enough. So what you have to do is count the amount of idleness or just sitting there not doing anything, and then figuring out who is working and say, you're the problem. Okay. And that's the technique called blame shifting. I should be able to do a demo on that. Okay, some of the new features. Let me ask you, how many people have ever used SPAC to install programs? Nick Romero has to raise his hand. I don't see where Nick was, but how many people have used SPAC? Okay, so we're now starting to use. How many people have ever built HPCToolkit from source? Well, good for you. Okay, Rashawn, yes, you. Well, good for you. So we're now starting to use SPAC to build our prerequisites. We have something like 15 or 20 prerequisites that are outside of our code base. So we're now using SPAC to install those. I have instructions written for this, but they're not. I haven't really announced it as, this is now the official way. It works and the pieces are in place. I just haven't announced and said, here, everything is done. So one of the things that I've done over the past year or so is we've added threads to the HPC struct. Now comes Nick. We've added threads to the HPC struct program. So HPC struct is the program that analyzes your binary to construct a control flow graph to compute the loops and the inline sequences. So we've sped that up by adding threads to that. And we've added a way of measuring the block time in the kernel. So if your program does like a lot of I/O or something, then when you call read or write, if you just sit there waiting on these events to happen, then we have a way of measuring that. Although, and that's called block time, but that's not what I guess I'm going to talk about today. And then some ongoing work. So ongoing for a long, long time is this effort to match up OpenMP threads with their master threads and attribute the idleness to the thread, to the call path where the OpenMP region was launched. We also have work in progress for GPUs. And then one of the things that we don't do quite so well is scaling to a very high number of processes and threads, which is going to be the next major effort. Okay. And so again, this was the picture you're supposed to have in mind. I have a few more reference slides for, I've installed HPCToolkit on Theta. So this, there's a reference for where the home web page is, where I've installed it on Theta, where it is on GitHub if you want to build it yourself, and most importantly, where to send questions to. That is not me personally, but you send them to the list, so in case I'm not the best person to answer the question. And I have a few extra, some reference slides for how to run beyond the manual. Some notes on Theta and some notes on the OpenMP tools library. Okay. So I want to spend most of the time now doing a couple of demos. So let's see if I get the right one here, if it hasn't disappeared on me. Here. Okay, so this is an example of what we call the HPC trace viewer. When we run your program and compute all the call paths, we can present this top-down and bottom-up, which is not what this does, but this presents it in a trace format, in a time sequence picture. So this is like a one-page map of the entire running of this program. Now, this program was the HPC struct program for which I've been adding threads to it over the past year, run on the NW-Kim binary, which is like 160 meg static binary for x86. So let me ask you, are there any NW-Kim developers in the audience? Only one wants to admit to it? Well, as long as I have someone to pick on. Okay, so this is what the program looks like at the very top level. Not surprisingly, the entire run of the program is in main. All the side threads are in basically, begin. What is it? Pthread start routine or whatever GNU calls that. Now, if we start moving down the call stack, we see some structure start to emerge here. Okay. So let me back up just a little bit and say, now, I said this was a map of one run of this program. Now, this is actually a three-dimensional picture. Okay, so two of the dimensions are pretty clear. So left to right is time, top to bottom is processes and threads. This is just a one process program, but it has 12 threads. I ran this on the login node of Theta on 12 threads. Now, can you guess what the third dimension is? The third dimension is the call stack. So the third dimension is represented by this table over here. So the process starts off in main calls real main, calls make structure, it calls parse, and then down, into the weeds. Down in here. Let's pick something where it's actually running over here or something. Whoops, let me show this. So this bottom pane shows you what the depth of the call stack is for that particular thread. Okay, now, since, I wrote this program, so I kind of know what it does. Let me see, I'll find the right depth. Okay, so the first thing I want to show you is the program. The program works in like 3 or 4 phases. So basically what HPCToolkit is doing is it's constructing a control flow graph for a binary, which gives us the loops, and then also asking for the debug information, which gives you the inline sequences, and then puts them together. Okay, now the first phase for this, so we wrote like half of this program, and the other half of the program uses a utility called Dynanst. Has anyone used Dynanst? Dynanst is dynamic instrumentation. Has anyone? So Ray Loy mentioned this with the stat tool. Stat is based on Dynanst. So Dynanst is kind of a cool tool. It allows you to rewrite program binaries at the binary level. So if there's a particular function that you wanted to instrument, you could intercept that function and rewrite the binary. So instead of just jumping into the function, it'll jump off into your code where you want to do something and then come back, and then the binary doesn't know the difference, depending on what your code does. Okay, so the first phase of this is reading the symbol table, open symtab, parse types or something. Now, reading the symbol table is based on elfutils. Elfutils currently does not support parallelism. We have a student, I guess a graduate student at Rice who's working on that, but for now, elfutils doesn't support concurrent access. So this is serial code. The next phase is parsing the binary for the control flow graph. That is, you have to identify all of the functions, you have to crack all of the instructions, and figure out who calls who. You have to figure out all of the jumps and all the control flow for the graph. And then once you have that as a graph, then you can analyze the graph and form the loop structure. Okay, and so that works in a couple of phases. And then the last part, so starting in this vertical line, so everything up to here is basically, say, call Dynanst and tell Dynanst to analyze the binary, and then from here to the right is the code that I'm responsible for that then makes calls to Dynanst and says, and then produces a structure file that combines the control flow graph with the inline code. So there are a couple of things, and this works in like 3 or 4 phases or something. So there are a couple of things I can show you about this. Well, first phase is serial, but if we look at the second phase, so this is the part of Dynanst that builds a control flow graph. Now this dark blue area, if we move down a little bit, whenever you see lots of little lines like this with all jaggedy colors, that means the program is calling functions, calling and returning, and doing a bunch of stuff. This green is barrier weight, meaning essentially idleness. And you'll notice, well, this is also idleness, just under a different name. So all right, so now it's on the same name. So you notice this thread, and this thread are very long, and these other threads, all finish nice, pretty close together, and these 3 threads stick out. Now, why is that? We need our NWChem developer. Don't run away. Well, the answer is Dynanst analyzes functions one function at a time. There's something like 42,000 functions inside the NWChem binary, and each of these 3 functions is larger than all the other, 41,997 threads combined. So, NWChem developer, fix your binary. Why do you have this one ginormous function, or 3 ginormous functions? Okay, so one thing this tells me is that if I want to speed up Dynanst analyzing a binary, see right now it operates under the simple rules of I analyze one function at a time. And then I just have a whole bunch of functions and I run them in parallel and whatever order I get them or something. So if I want to crack this, if I want to reduce the size of this spike, then what has to happen is Dynanst has to analyze the inside of one function in parallel using threads. I can't crack this any better until I start adding threads analyzing a single function, which is actually hard. If I go back to the top, let's see, you took away, that's odd. I see, that's unfortunate. Your screen sharing is stepping on top of real estate that I need here. Okay, so let me change this so that I'll do full screen in a different way. So I need this button, the home button. So so this is the entire program, and if I go to the part that I'm responsible for and just look at this, if you'll see that there are also 3 spikes here. The very first function, and then these 2 other threads are also disproportionately larger than everything else combined. So and again, it's for the same reason that the function the program that analyzes the results from Dynance and puts them together, it works on one function at a time, and one function is done serially, and you just break up by function. So if I want to crack this, again, I have to analyze functions in parallel, which is hard. Okay. This middle section is all barriers, so this entire region here is all serial code. There's this is all part of the parse function, which constructs the control flow graph. There's one section of parse which is called parse finalize, and parse finalize is not parallelized. So to improve this section, I'll need, the Dynance people will need to start adding threads inside finalize. Okay, so the trace viewer gives you a nice sort of overview of your program. I can see the entire run in one frame. I can figure out the phases. I can see some features of this. Okay, so let me show you the same program run. Okay, so this will be the same program. Where are we? In the viewer. Okay, so let's see, am I going to need, okay, I think I may be able to get away with this. Okay, so this is the same program just where I'm showing you the tree, the tree in a top-down fashion. So one thing to notice is that the program root, which is main, is 9% of the program, and the thread root is 91% of the program. Now, this is what I call the physical view of the program. So this is what the program actually does, in the sense that that you have one main thread, which main calls something, which has the call stacks that you want to see. All of the side threads start off in whatever pthread start routine you have. Okay, but they're separate. They're separate call paths or something. So that's why if you just look at main, which gives you better call stack. So let's open this up and see where we are. Okay, so main, and here is main up here. So main calls real main inside of a catch block or something. Here's the definition of real main. Real main calls make structure, which is the entire program. So this is where it calls make structure. Here's where make structure actually is. This is the beginning of the make structure program. This is the main loop of main structure where it analyzes all the pieces. If I open this up, then what I see are the different phases. So so all of the time spent just in the main thread only adds up to 9% because I ran this on 12 threads, and you have the other 91% are all in the side threads. This first section is calling dynance, calling to analyze. But what I can see here is, so among the 9.3% of the time spent for the main thread, 5.7 of that is spent calling dynance and having dynance analyze the binary. And this, oops, I have to. So 5.7 is for parsing the control flow graph, and of that, this part that I said it was the serial phase, dynance parser finalize is 2.9% or something. So I can start at the top and I can walk down the tree and I can see how much time is attributed to each function, and I can expand and contract nodes or something. But, oops, let's see, I closed the wrong thing. All right. But these are the main phases of the function with the times attributed to them. The time spent in dynance. This one is actually the time spent in my code, where we go make structure, we go to a loop, we go to one work item, another loop inside that, and then analyzing individual pieces until you get smaller and smaller functions. Okay. Now there's one interesting thing I want to show you in this. So here's one parallel region. Let's see. So this is a parallel region. Now this analyzes the line map information inside of dynance and stores that. So dynance stores the line map information inside in boost objects. So this is parse line info. Oops, sorry. Inside of or inside of one loop, inside of another loop. And we get down to the dynance function, add line information, and add line information calls, or it doesn't really call, it uses a boost template insert, which uses the boost object final insert, which is the boost template, what is it, insert underscore, another boost template, another boost template, another boost template. And finally, if you get all the way down to the bottom, we get down to the operator new, the new operator inside of C++ through something like 10 levels of boost templates. So how many people have ever used boost in programs? Have you used boost? Well, you'll know that boost uses an awful lot of templates. And so this is one of the things that the HPC struct program does, is show you all the steps of the templates. If you want to see what one individual step looks like, so here's multi-index. This is the entire full template of this one inline call for boost multi-index, until you finally get down to operator new, the operator which is C++. Okay, well, let me show you a different demo that does a couple of things in a more interesting way. If we find, let's see, where is, I need to get back to the trace view. Oops. Okay, so this is a different application. This is the AMG 2006 program, which is one of the Coral or something benchmarks, something to do with measuring throughput and flops or something like this. Now, most of this program is set up. So all of the main program is set up, and almost all of it is serial code. So if I zoom in and look at one section, so this is one thread, the main thread doing the setup phase, and all the side threads are just sitting here idle, which we represent by comp idle. But people don't care about the setup phase. They only really care about the solve phase. So if I zoom into just the solve phase, so the entire benchmark for this program is only based on the solve phase. Why they couldn't, speed up the program like a factor of 10 by parallelizing the setup, I don't know. But if we start to zoom in, what we will see is we'll begin to see iterations of the solve phase. This, and we can start to see kind of a regular pattern here. So let's zoom in on just one rank. So this is like 1.5 iterations, okay. And if I select this is OpenMP, this dark blue is OpenMP region 23. Now, one thing you'll see here is that so this top line is the main thread. So if I look, if I look at the crosshair here, well, it tells me the entire rank here. This is rank 5, going from rank 0 to rank 16. So I ran AMG on 8 MPI ranks and 16 threads, and this is rank 0, rank 15. Now, one thing you notice is that down in the side threads, the call stack for all the side threads look like main calls solve function, calls solve, calls cycle, calls relax, calls OpenMP region. Now, that was not the case in the first demo I showed you. So what I call the first demo was just a physical view where the main thread has a different call stack from the side threads because the side threads all start in pthread create or pthread start routine. So what I've done here is add extra machinery to match up the call stacks for the side threads to where the master thread is, and paste it, and take a tree and graft it onto the tree of the master thread. And this actually requires a lot of machinery. It requires editing the OpenMP library. And this will become part of the standard in OpenMP 5, if and when OpenMP 5 ever, officially happens. We've been waiting for years. But one of the things to show you, if we zoom in on one OpenMP region, so here, so this dark blue is OpenMP region number 23. And let's zoom in to where we have just OpenMP region 23 and nothing else. So that's pretty close. Now, what do you see about this? So the dark blue is OpenMP region number 23. It doesn't have any subfunctions. It just has, loops and stuff inside of it. And the green region is idleness. So what do you see? What's the problem here? This is an example of load imbalance. So I have half of the threads spending a lot of time working, and then these bottom 4 threads that finish in 40% of the time. So if I click on summary view, I can hover the mouse over here, and this gives me a measure of I'm spending 76% of the time working. Well, let's see. Let's click here. So I'm spending about. Let's make this a little bit more. So the dark blue is OpenMP region 23, and I hover here, and that's about 76% of this zoomed in rectangle, which is one iteration of one OpenMP loop, and then the green is 24% idle. And over here, this is the call stack that got me to here. So if I go back, see how far can I go? Well, I guess I could zoom in again or something. All right. So this was. So it was this blue region that that we said had about 75 or 76% useful work and 25% idleness. There are other sections in here, like this one is OpenMP region 8. So this one looks a little bit better balanced if I zoom in on, oops. If I zoom in on just it, then this is like 90% working, and this is about 9% idle or something. Okay. But again, this gives me a nice sort of overview of my program, and you know, when I zoom in, I can look for things like load imbalance or something. And see, one of the things that having the trace view will show you is now this particular program doesn't really have. This demo doesn't have this particular problem. But if you had an example of several threads or MPI ranks that all came up to a barrier and they were all jaggedy, you know, some arrived at the barrier very quickly and some took a long time, you know, you would see that. But more importantly, you could see what happens right before the barrier. So you can see where are they spending, you know, in what function and what call path am I spending time before I get to the barrier, which is the real problem. I mean, spending time in the barrier is not, you can say this rank spent a long time in the barrier, which is useless, but that, again, that's not the problem. The reason that the barrier takes up time is because somebody else was late to the barrier. So that's what you really care about. Okay, so let's look at the same demo in a different form. Okay. And again, I think I can get away with this. Okay, so this is the top-down tree, the calling context tree, remember the picture I told you, of the same program. Now, you may notice a little bit different, something a little different here. So I have, instead of having the program root and the thread root, well, there is a thread root, but there's just a few stray samples. So the program, well, I don't want all of this. So the program root is main, and, well, I'm going to have to close this up. And the other main, the other sort of root node is comp idle. So what we've done here is by using the OpenMP library, we've grafted all of the trees for the side threads as if they were part of the main thread. That is, as if main called something called OpenMP region, and you took all the counts for all the side threads and added them to the main thread and put this under main. Okay. Now and we've also counted columns here of OpenMP idleness and OpenMP work. So if I start expanding main, now you'll see that the time, this is the setup phase, so the time for the setup phase is 47% out of 51%, but it consumes 93% of all of the idleness. And again, the setup phase is mostly serial code, but what people really care about is the solve phase. Okay. So this is where the program calls solve, and that's where solve is defined. And if I expand this a little bit, so the solve phase has multiple pieces, and I zoom in a little bit more. Okay. And I zoom in a little bit more, and I come down to here. Okay, so here's the call path that got me to OpenMP region number 23. Okay, this is the one that we said that had somewhat load imbalance. You go through a couple of solve phases, a loop into the AMG relax, and then inside a parallel region, and then finally into the OpenMP region. Now, one of the columns that I've written here on the far right is, well, first of all, this column is the amount of time spent in this function. This column is the amount of idleness attributed to this node in the tree, the amount of work in the tree. Now, let me just remind you, the rules about idleness are, it's not the case, that main calls solve, goes into a loop, goes into AMG relax, goes into a parallel region, and the parallel region just calls, oh, let me call OpenMP idleness. No, that's not how it works. You don't just call OpenMP idleness. You run an OpenMP loop, and then sometimes the threads are idle, but for the threads, while they're idle during this loop, we charge that to the loop. We charge this to the working call path. Okay, so what I've counted here is this column is the amount of work that it's doing. Well, this column is OpenMP work. This is the amount of time that it's spending, and this is the amount of idleness that it's taking. And this last column, this is what I've computed as a derived metric. So I call this parallel efficiency, and parallel efficiency is the amount of work, OpenMP work, divided by work plus idle, and then scaled to 100 and displayed as a percent. Okay. So what I can see is for this OpenMP region, which I get to in this path, it has a parallel efficiency of 78%. So if I go to the very top in main, my overall parallel efficiency is 52%, but that's really a very misleading number because that includes the setup phase. There were other things I could have done to measure only the solve phase, but I didn't do them in this run. But if you see in the setup phase, it only has, well, again, 52%. But the solve phase, as the overall as the entire phase, this has about 71% parallel efficiency for work. And what I can do is I can go down for each piece. Let's see. So I can look at each piece of the solve phase. I can look at this function with 81% parallel efficiency. That function is 64. This one is 66. I see. So that's why it's called seq. Sequential vector copy. It only has 6% parallel efficiency because it must be sequential code. And again, I can go down to each individual OpenMP loop and measure the efficiency of how well that loop is doing. So this is what I told you before that might not make so much sense, but sort of basically everything that we present in this tree, we do it on a per node or per node in the tree basis. So I've computed parallel efficiency by this formula of work divided by work plus idle, but that applies to every node in the tree. So it's not just a single aggregate number of your program is 85% efficient. It's for each step or each scope level. I get a separate number, and some are good and some are not good. So this would tell you what to work on. Okay. Well, that's kind of the whirlwind tour of some things that we provide. So let's finish here essentially on time and give Catherine her chance.